Okay, we are at noon Central Time in the US, so we can start with our seminar. We are just gonna keep admitting people into the seminar who are currently in the waiting room. But I would like to welcome all of you here to our seminar, and we're very happy to have Ken Forbus present today his talk. Before I introduce him, I would ask Matt if he would like to introduce the regulations and the housekeeping of our seminar today.
Yeah, hello everyone. Sorry, I'm just trying to, there we go. So a bit of housekeeping before we start. So we've muted everybody's microphones for security reasons. And we'd ask you if you could turn your videos off as well, unless you're speaking, just to keep the connection stable. However, we would like this to be an interactive session. And so if you'd like to ask a question, you can either use the chat at the bottom. So there's if you go to the bottom of the Zoom screen, there's a chat icon, and if you click on that, a chat window will open up, and you can speak to somebody directly, or you can speak to the whole group. And also, at the end of the talk, Ken's talk, will be if you could use the raise your hand feature. So if you go down to the bottom where it says participants, and you click on that, a window on the right-hand side of the screen will open up with all the participants, and there should be an icon at the bottom for raising your hand. So if you press that, you go to the top of the list, and either myself or Margarita will turn your microphone on and invite you to ask a question. And if you'd like to, you can turn your video on as well. So just to bear in mind, we are recording this session. So, and I think that's pretty much it. Ken has asked if you could, if you have urgent clarifications, feel free to raise your hand during the talk, but if you could keep any more substantive questions to the end, that'd be appreciated. So I'm going to pass you over to Margarita now, who's going to introduce today's speaker.
Thank you. We are very happy to have Ken join us today for the seminar. Ken Forbus is the Walter Murphy Professor of Computer Science and Professor of Education at Northwestern University. He received his degrees from MIT. His research interests include qualitative reasoning, analogical reasoning in learning, spatial reasoning, sketch understanding, natural language understanding, cognitive architecture, reasoning system design, intelligent educational software, and the use of artificial intelligence in interactive entertainment. He is a fellow of the Association for the Advancement of Artificial Intelligence, the Cognitive Science Society, and the Association for Computing Machinery. He has received the Humboldt Award, has served as chair of the Cognitive Science Society, and was the inaugural winner of the Hobart Simon Prize for Advances in Cognitive Systems. And today he's going to give his talk for our seminar.
Well, thank you for that kind introduction. Everybody can hear me, yes? Good. All right, so I'm going to tell you about analogy and cognitive architecture. And I'll start out telling you what cognitive architectures are. Hello, there we go. I'll start out telling you what cognitive architectures are. And I'm going to argue that analogy is actually central in the cognitive architecture we're building. Then I'll talk about three things that are explorations on how this architecture works. One is modeling conceptual change, and talk about some work by Scott Friedman, which has been used to model several phenomena in human conceptual change. Then I'll look at learning by reading and how to read instructional analogies. And then analogical question answering training, where we show that analogical learning can provide human-like data efficiency and the ability to learn from unlabeled training data, unlike what most machine learning systems require. And then I'll wrap up with where we're going next. So the thing about cognitive architectures is they're trying to model larger swaths of mind, multiple aspects of cognition in the same system. Now, this is in contrast with the usual way of modeling things, where you have a particular process that you're modeling, and now you make up the inputs, and you hand evaluate the outputs. And the problem with that is it leads to what's called tailorability, because I'm controlling this and controlling this and controlling this. Often you can make things come out for reasons that aren't actually realistic. Whereas if you have this process embedded in a whole bunch of other processes which are providing inputs automatically and doing something with the outputs so that you're showing they're actually useful for something, then you reduce tailorability and you have more confidence that the processes you're modeling are actually being modeled in a way that's going to be useful. So think of it as it's the same system viewed as a program, but used in many tasks. Now, cognitive architectures go back a long way. SOAR and ACT-R started in the 1980s, and their focus was on skill learning. And they still, in fact, do a lot of work on skill learning. SOAR is heading more towards trying to achieve human-level AI. ACT-R is heading more towards explaining neuroscience. But neither of them really worries about the kind of human conceptual structures and the kind of reasoning that we're doing in companions. By the way, these systems are also being used in applications. They're non-player characters in computer games and simulations. They've been used in physical robots. So if you look at where AI is going, cognitive architectures is going to be one of the big revolutions in AI, I think. Now, our approach in the companion cognitive architecture is to create software social organisms. And what we mean by this is systems that work with people using natural modalities. Most of the time we use natural language and sketching. Recently we've started adding speech and vision. I'll show you an example of that later in this talk. The systems need to learn and adapt over extended periods of time. They need to keep up with their human partners, and they need to maintain themselves. If you have a human assistant or a coworker, they don't blue screen, and you can talk to them to update their model. That's really important. Now, why social organisms? Well, Lev Vygotsky pointed out in the 1930s that much of our knowledge is actually learned by interactions with other people. And to be sure, there's lots that learned by dealing with the physical world. I pick up a pen, I know how to manipulate that, that's great. But on the other hand, there's also cultural knowledge. So many things we understand we've never directly experienced. So the American Revolutionary War, for example. If any of you experienced that directly, I would love to talk to you offline, because that means you've either invented immortality or time travel, and either would be extremely interesting. Okay, so we get all sorts of models from our culture, and that's something any cognitive architecture has to model. Now, we have two core hypotheses. A lot of this work is in collaboration with Deidre Gentner, a cognitive psychologist, and we use her structure mapping theory of analogy. I'll tell you more about that in just a moment. But her point is that analogy is used throughout human reasoning and learning. And by throughout, I mean like vision, problem solving, conceptual change, all throughout. And you'll see a lot of examples of that computationally in this talk. And the kinds of representations over which analogy is done are often what we call qualitative representations. Qualitative representations take the continuous stuff in the world and turn it into discrete symbols, into meaningful pieces. So qualitative representations form a bridge between perception and cognition. They also provide the representations needed for common sense reasoning. If I throw something up in the air, you know it's going to come down. You don't know how long it's going to take, down to the microsecond, because you don't have that numerical data. Qualitative representations let you reason quickly with very little information. If you want to see more about how qualitative representations are used in human cognition, I could give a whole talk about that, but I recommend the book I just wrote on the subject, which actually looks at both what the qualitative reasoning community has done, but also with an eye towards explaining human aspects of human cognition. So, now, structure mapping theory. So the idea is that analogy and similarity involves correspondence between structured representations. So in this description, for example, this is one description being compared in green. These representations, by the way, are automatically produced by a natural language understanding system. You'll see how that works a little bit later, as are these. And so this is an analogy where someone is using a leaky water bucket to explain how a leaky house loses heat. And so the idea is you have these structured relational descriptions, and a mapping includes correspondences that say what goes with what, and a numerical similarity score telling you how good the analogy is. Notice if you have similarity defined as a dot product of something, you just have a number. You don't really know what goes with what. That's kind of implicit in the vector, matrix, or tensor. With structure mapping, we actually compute what goes with what. There's a large body of psychological evidence for structure mapping theory, and again, that evidence ranges from medium-level vision up through reasoning and conceptual change. Now, candidate inferences are cool because candidate inferences provide a form of pattern completion. Here, this relationship of something being the object of a state change is being projected into the target based on the correspondences. This can hypothesize new entities, and these conjectures, of course, don't have to be valid, but they provide a way of inferring, they provide a way of transferring knowledge. Now, computationally, this is done by the structure mapping engine, which takes two propositional representations as input, some optional constraints if the task provides them. These are typically requiring or excluding correspondences. We only give it a very limited language of constraints to work with. And it operates in polynomial time by exploiting the graph label, i.e. the semantics of the structure, and a greedy algorithm. So it produces a mapping, including candidate inferences. And the way it works, the way it does this is pretty interesting because it actually makes psychological predictions too. So SME starts with a base and target. And the first phase, you construct this network of match hypotheses, which is inchoate, it's inconsistent. It's just everything that might match locally. Cause here, cause here, cause here, cause here. Sure, why not, right? Put in a match hypothesis to all three. You don't know which is going to be right. The one-to-one constraint of structure mapping says they can't all be right, but you put that off. The second phase is you actually evaluate the match hypothesis network. You start figuring out what things can and can't go together. And at the end, you end up constructing mappings, which are structurally consistent collections of these things. Now, why does this matter? Well, for example, Dedry and her colleagues have found that you can look at metaphor interpretation like this. So my job is a jail. Fine metaphor, right? My jail is a job. Not so good unless you're a prison guard. Okay. Now, if I tell you both of those things, one of those two things, and I stop you 600 milliseconds in, you can't tell them apart. Let you go for a second and a half, you can. And the reason we think this is happening is because in 600 milliseconds, you've only gotten this far. And you see a big description. That big description says, hey, there's probably something here. And it's only when you have more time that you figure out, in one case, you've got some juicy inferences in one of them and not in the other. And so that's an explanation that falls out of how SME works. Now, of course, that's just the mapping process. There's also retrieval and generalization. Those are basically additional small complexities to the way mapping works. So here's a kind of cartoon version of how it all fits together. So the structure mapping engine is matching. I have some new description I'm trying to reason about. I retrieve something from memory somehow, and SME says, well, here's some inferences I can carry over. Now, the thing it retrieves may be an example or a generalization, and those are retrieved by a model called MACFAC, which stands for Many Are Called, Few Are Chosen. And so it's doing a first stage, which is based on predicate overlap. Think of it as an estimate about how big that first match hypothesis forest stage is. And then that second stage is actually using SME. Now, this knowledge base has a whole bunch of semantic information, but also a ton of experiences and generalizations that are incrementally built by experiences. That's constructed by a model called SAGE, Sequential Analogical Generalization Engine. And that basically uses SME to mush together descriptions and keeping the overlap. Now, since I'm putting together descriptions and I know what goes with what, then I can start producing probabilities. 60% of the time, the swans are white. 40% of the time, given the way the world is today, the swans are black. Lots of black swans in today's world. And so the generalizations that are produced are probabilistic. They're partially abstracted, but they don't have logical variables by default. So this is the essence of the companion cognitive architecture. You have these operations, And these operations are important because you look at most cognitive architectures, they say, well, you got data, you got rules. And there's not a lot of room for distilling knowledge from experience. But Readi and I think it works something more like this. You've got a vast number of experiences, humongous, and they're concrete. You're constantly going around in the world, you're reading stuff, you're talking to people, and those are giving you experiences. And what happens is, as you use SAGE, you get descriptions of increasing portability. That is, you get some less and less concrete knowledge, more and more abstract knowledge, and all along the way you can put it to work, because instead of using logical unification or some kind of production rule pattern matching, you're using analogy to apply these intermediate forms of knowledge to new situations. Now, the first thing I'm going to talk about is modeling conceptual change, and in fact, this is the place where we've pushed on this model the hardest. So in modeling conceptual change, you start with raw experiences, you produce generalizations from those, you distill those into conceptual models, and you refine those all the way to expert models, F equals MA and its friends. And we've done work at each one of these levels and moving between the levels. I'm going to focus on here, actually these two, because these are really interesting demonstrations of how analogy can be used to model conceptual change. This is work by Scott Friedman on his assembled coherence theory. Here's the idea. You have some phenomena you're trying to explain. So you retrieve prior experiences along with their explanations. Now the qualitative models you use in explaining those prior explanations are now applied to the new situation abductively. You get several explanations, you score them, you pick the best. If inconsistencies arise, you get new data that says the model you picked is wrong, then you search the space of models to provide a better explanation, and you store that new explanation and situation back into memory. Now, here's an example of that model being used to explain something. Mickey Chi had this lovely experiment where she was looking at self-explanation and how important it was. And these are models of the human circulatory system. The correct model is the double loop model here. And each of these are different models that she found participants in her experiment had. And so in the read twice group, they got a description of the correct way the circulatory system works. And each of these arrows indicate, well, this arrow indicates of the two students stayed with this model, one moved to this partially correct double loop model, okay? And you notice that not very many got to the correct model. Whereas if they have to explain to themselves what's happening at every step in the explanation that they're reading, if you explain it to yourself, then in fact more of them get to all the way to the correct double loop model. So that was the original human subjects experiment. Now to simulate this, Scott produced models for each of the misconceptions, and then the predicate calculus equivalent of reading that text. And what he showed that if he varied the preferences used to score explanations, then he could actually explain 90% of the student transitions from one model to the other. So that's a way of saying, hey, look, the way I'm scoring explanations here actually does seem to have something to do with the way humans are explaining stuff. Now, here's the case where you start with the model and you get to a final model. What about building a model from scratch? Well, Scott also looked at modeling force and motion. And here he used sketches. This is a sequence of sketches drawn with CogSketch, which I haven't brought up yet, but I will. I said we did sketch understanding. This is an example of sketch understanding. And so this little cartoon shows a sequence that would be like a set of qualitative descriptions that someone would have computing from motion. And so we had a set of these things. Now, not a huge set, okay? This is like distilled high-octane fuel for someone learning. And interestingly enough, you have this companion run through this, and In the learning sciences literature, where the human data comes from, they use a series of sketches to test misconceptions. So, of course, Scott did the sketches in CogSketch and ran the same experiment on it after every piece of data. So, for instance, at one stage in CogSketch's, in Companion's understanding, you could ask it, is there a force on the book from the table? And, of course, we all say yes. But at some point, little kids say no, because if there were a force, the book would be rising, and it's not. Okay, and a companion actually falls for the same misconception early on in its learning. Now, if you track the models compared to human models, so this is a description of human mental models over time, right? So this is a list of models, and here's the number of people who have those models as you measure them in different grades. The circles here is, well, companion started out here, no force concept, and in 8 out of 10 simulations, it got to an internal model of force. In 2 out of 10 simulations, it got to an internal model that's not size, where size matters. And you can see that the sequence of models it went through is aligned with the sequence of models that humans went through. So it's capturing something interesting about the way human conceptual change works. He did several other examples. I'll show you just one more because it's hilarious. So the day-night cycle. Okay, here's day. And this is work by Stella Vosniadnu. So one explanation is the moon blocks the sun. That does happen. They're called an eclipse, okay? But that doesn't happen every night, right? And then there's clouds block the sun. Yeah, not too bad, except they've got to be really thick clouds and they've got to happen every night. The third model is, well, the sun just shuts off. Click, you throw the switch and off it goes. The fourth model, I love this model, it's that the sun goes inside the earth. And when you look at a sunset, you can see it happening. There it goes inside the earth. Got to be it. But no, the more boring one is the earth rotates. Now, you can tell kids the right answer and it doesn't stick. So what do you do? Well, Stella is Greek and the kids were Greek. So she hit upon an analogy, hieros, okay? So the sun is the flame, the earth is the meat, the rotation of the earth turns different sides of the earth towards the sun, and when it's facing the fire, that's day, and when it's facing the way, that's night. Voila. Now, it turns out, if you start a companion out with each of these models, and you give it this analogy, it always moves to the correct day-night model. So it is capable of taking correction via an analogy in ways similar to how humans are doing it. By the way, I mentioned that candidate inferences are conjectures. So the candidate inferences include the correct model. They also include that the earth is made of something like beef or something like lamb, okay, which isn't exactly right. Okay, so that's conceptual change. Now, what about learning by reading? A common use of analogy is to instruct people in text. So this is from a book on solar energy. You have someone explaining how a house with insulation that's imperfect is like a bucket with a hole, right? And so these leaks are like those leaks. Now, if you're going to read instructional materials, you have to be able to understand the analogies that are contained therein. So David Barbella tackled this by creating a model of analogical dialogue acts. You know, speech acts, communication acts are the interpretations you place on something in order to help you understand it. Well, analogical dialogue acts are a specialization of the informed speech act that help you process analogies. Now, let me divert for a second to show you how our language understanding model works, because it's very different than you typically see these days. So our focus is on deep understanding. We use an off-the-shelf parser and a packed semantics builder based on a theory called discourse representation theory by a couple of really clever guys from the Netherlands. We have a large knowledge base, whose contents I'll bring up at the very end, a large-scale lexicon, and we have an abductive semantic interpreter that if there's task constraints, helps, and if you don't have task constraints, well, you can still produce formal representations of meaning. So the idea is we're producing not just a parse tree, but we're producing representations that support inference. So we use the OpenPsych ontology, so we have a broad range of events. We can handle logical numerical quantification. So the heart has 4 chambers. You could say chamber 0, chamber 1, chamber 2, chamber 3, and make 4 little tokens here, right? That doesn't work for the brain has 6 billion neurons, right? You don't have 6 billion of something. And so being able to say, I have a set of things whose instances are neurons, and there's 6 billion of them. That's an example of numerical quantification. Quotation, if you're dealing with moral decision problems, quote, go ahead with the program, I don't care about the environment, end quote, says the vice president. You have to be able to handle that. Counterfactuals, if a dam is open, 20 species of fish will become extinct. So we've actually used this system in learning by reading, multimodal learning by reading, moral decision making, and even some of conceptual change modeling has used this system. So what happens when you get a piece of text? Well, so we have OpenPsych for things like events. So the word cools denotes a cooling event, and the grammar says, well, the solar panel cools. Well, that's the subject, so the object of the state change is this thing. That's a discourse variable, and we know from the definition of solar panel that it's a solar collector, okay? And so it basically grovels over the sentences, doing both lexical and syntactic and semantic analysis to construct these meaning representations. Now, on top of those are the dialogue acts. And so the analogical dialogue acts basically identify the roles statements play in an analogy. So if I step back and say, well, okay, I read this analogy and I go back and say, well, okay, this tells me there's an analogy. It's introducing a comparison. The wall is like a hole in a bucket. And now the target, the thing I'm trying to learn about, is the wall. And so this is going to be connected to the wall. And this is talking about the bucket. So it's extending the base. And I actually say what some of the correspondences are. I say what some of the inferences are. So I'm not going to walk through these in gory detail because that would take too long, but I'll just show you one example. So introducing a comparison. The wall is like a hole in a bucket. Well, the is like is a signal, and that says, well, okay, I've got the target and base, and so anything that connects to these and these are going to be glommed together. And in fact, you go off and grab more information about those elements from long-term memory. And because the person said you're supposed to compare these things, you actually add a constraint to the comparison that says, hey, wall goes to hole, okay? I mean, there might be better analogies purely structurally, but the instructor intended it to go this way. And so you want the system to do that. Okay, so now the reader knows how to look for the other dialogue acts and assembles the descriptions. Now, can you actually learn this way? The answer is yes, otherwise I wouldn't have brought it up. So David took 13 example texts from multiple domains, about 13 sentences per text, each of them describing an instructional analogy. And so if you look at the descriptions, you know, on the average about 16 relations per case, about 23 attributes per case. So these are pretty reasonable descriptions, and get automatically produced. And graduate students who were not David looked at those analogies and proposed questions that would be reasonable for someone to be able to answer based on those analogies. So 22 textbook style questions. And we used a 2x2 design with and without analogy, with and without background knowledge. And amazingly enough, with analogy, in fact, the system did better than no analogies. And with background knowledge, in fact, it did better than no background knowledge. And it's not like the background knowledge actually just provided the answer. If you look closely, the background knowledge improved mappings which let it get things that it couldn't have gotten otherwise. And all the failures were missing answers, not incorrect answers. So we take this as a really positive thing. Now that's text. Of course, there's more than text in the world. So how do you deal with visual materials? Well, CogSketch is our model of high-level human vision, and it uses analogy, as you might expect, and qualitative spatial representations. If you download CogSketch, you'll have a full set of these geometric analogy problems. A is to B is C is to whatever, and the CogSketch model will show you the method it uses to solve them. And in fact, it predicts human reaction time differences in doing these geometric analogies. There's an oddity task due to Dahan and Spelke where they looked at differences between Americans and Munduruku. Munduruku is an indigenous Amazonian group. What's hard for the software is hard for people and vice versa. And by doing ablation studies on the software, obviously not the people, you can actually come up with explanations for what some of these cultural differences are. Raven's progressive matrices is by far the single best test for human fluid intelligence. The CogSketch Ravens model is in the 76th percentile, making it better than most adult Americans. And again, what's hard for people is hard for the software and vice versa. Andrew Lovett has also extended this to handle 10 classes of paper folding tasks, looking at spatial abstraction models in human performance. And that link on the bottom, by the way, is where you can download CogSketch and give it a try yourself. Now, if you have an understanding of visual materials and text, you can do multimodal learning by reading. So Maria Chang, as part of her thesis, took a dozen or so analogies from a book for middle school teachers. And so a cell is like a city, and it goes on to explain the analogy. And she also drew sketches to go along with these things. Here's City Hall, the wind plant, mitochondria, okay? And now the cool thing is you use analogy to fuse the understanding of text and sketch. So Mayer's multimedia theory says, take your understanding of the text, take your understanding of the diagram, and align them somehow. Well, it was Kate Lockwood who looked at that and said, hey, align, use SME. And in fact, Kate was the first person to do that. Maria built on that. And so she had the understanding from CogSketch of the diagrams, which got aligned, and the understanding of these that got aligned. But to do the fusion, you use it within the same description. So using analogy a lot to understand these things. So now with the analogical dialogue acts, you can pull out things like, well, the mitochondria like power plants, the mapping says. So if someone asks you, what do mitochondria do? You can infer they produce energy. And this companion using these ideas was able to answer 11 out of 14 questions from elementary school science tests based on what it learned by analogies. Okay, so now we're going into our last big new thing being done with this stuff. And let me step back and give you a bit of perspective on natural language understanding, because if you're not an AI person, you may not, this may not make sense to you. So in machine learning, there's a sort of popular press notion that it just learns, it's magic. But in fact, you hand engineer massive data sets, usually with annotated data. You hand engineer the hyperparameter search. Inside Google, this is called graduate student descent, right? A play on gradient descent, okay? And these can give you impressive results on multiple choice questions. They often fail miserably if they have to generate answers, and they're very brittle. The same kind of adversarial attacks that you see on computer vision models that use deep learning also happen for the things that do question answering. Now, our approach is really different. So our approach is high precision understanding. So instead of hand engineering massive data sets and hyperparameter search, we hand engineer a massive knowledge base. Well, actually, we get it off the shelf, and you can too. There's no reason to build one from scratch these days. Come back to that at the end. Hand engineered grammar and algorithms, and we get impressive results on questions where you have to actually generate the answers. All the things you've seen before are not multiple choice. The system actually has to generate the answer, and has to be able to explain it to us if we ask. And currently, they're hard to scale. So how do we handle the scaling problem, which is our bête noire? Okay. Well, Analogie to the rescue again. So we've got this general purpose language system, and what we'd like to do is adapt it to new domains. So how do you do that adaptation? And we want to do that adaptation without annotated data, because humans don't need annotated data to learn, and with high data efficiency. I shouldn't need many examples, ideally just the same number that people do. How do you do this? Well, here's what we do. So you start out with question-answer pairs in English. Okay, sorry if English isn't your native language. We are who we are. And so you start out with this question and the answer, you run them through the natural language system, and that produces multiple possible interpretations for each. And that's okay. Because you know that somewhere in this space, there is an interpretation of the question such that for some set of interpretations in this space gives you exactly these answers. So you use a connection graph search through concepts in the knowledge base to connect these things up. And that lets you construct what we call query cases that can then be applied by analogy to interpret novel questions. There's a really common thing called Geoquery in machine learning, which is a question answering task. It's a small data set of US geography facts. Now I'm going to show you real live results, okay? I'm going to show you just how insanely data efficient this scheme is. One training question. Which capitals are in states that border Texas? Now, Texas is unambiguous, but capital could mean money, could be a geopolitical thing. State, state of matter, solid, liquid, gas, okay? But given Baton Rouge, Little Rock, Oklahoma City, and Santa Fe, in fact, the interpretation that makes sense is capital is the geopolitical one and state is the geopolitical interpretation. Okay, now, second training question. Okay, what rivers are in Utah? Colorado, Green, and San Juan. Well, San Juan is a city as well as a river. Green is a color as well as a river. Colorado is a state as well as a river. But the only one that makes sense are the ones where these are rivers. Okay, just those two. Two training questions. I dare you to try this on a deep learning model or a standard statistical machine learning model, okay? Now, what rivers flow through states that Alabama borders? Works fine. What are the cities and states through which the Mississippi flows? Works fine. What are the cities and states that border states through which the Mississippi flows? Just fine. In other words, if you have compositional representations in the query cases, you basically are applying those by analogy to ever more increasingly complex questions. Now, how does this add up? Well, if you look at typical machine learning systems, they require about 600 training examples to do decently on Geoquery. Now, since our system is explainable, we can look for any question it answers and says, here's why it got that answer. We can have a system automatically inspect it. We just train it through the usual training test splits. We can have a system go back and analyze it and say automatically, here's an optimal training sequence for Geoquery, because we know which analogies got used in what order. So we can get comparable performance with only 50 examples. You know, so that with just 10, we're already almost at 60%. By the time you get to 50, you're basically at state of the art. Now I should mention this is not the most data efficient thing we've shown. On link plausibility, by a few careful tweaks, we get state-of-the-art performance with several orders of magnitude less data on that task. So analogical learning is insanely data efficient. Now, one way we've put this to work is by an interactive kiosk. So this is analogy on the hoof, analogical question answering in daily use since fall 2018. If you can get into the building now, given that we're all locked down, but someday you'll be able to get there. Again, you'll walk up and you'll see this kiosk. It's got a camera and a microphone, speech recognition, and it's basically looking for you to interact with it by voice. And here's a sample interaction. So who teaches machine learning? Doug Downey is the instructor. Where is Downey's office? Located in MUD 311. It actually puts up a map, okay? So this is done using analogical question answering, the same language system, full stack, while the person's standing there doing analogical retrieving, applying query cases, constructing a query, and answering it. The training only requires 11 question answer pairs per question type. And by the way, we can probably do that more minimally if we wanted to, but we haven't bothered. And it takes a whole 5 minutes of clock time to train on a tablet computer. Okay, as opposed to, let's use whole data centers, massive numbers of GPUs to train traditional machine learning systems. So this is really robust and really data efficient, much more like humans than like machine learning systems. So let me step back and close up here. So analogy permeates cognition. It's used in visual problem solving, it's used in language understanding, it's used in conceptual change. In fact, it's also used in theory of mind, referring expression resolution, learning linguistic instructions, analogical training for common sense reasoning, a lot of things I didn't have time to talk about today. And these structure mapping models of matching and retrieval and generalization, we've argued, can play a central role in cognitive architecture, and these experiments lend some credence to that. They're broadly compatible with human reasoning and learning. Now, one of the things we're doing now is we're basically saying, well, here's this continuum of knowledge model. Does it work outside of physical domains? Well, one answer is social reasoning is like physical reasoning. So the same mechanisms, but you have more complex representations like nested beliefs. So experiences up to generalization and conceptual models. Irina Rabkina just finished her Ph.D. thesis on the analogical theory of mind. Those are lovely papers that explore how to model how it develops, as well as how to use it to understand other agents in simulation. Taylor Olson is working on learning social norms through conversation. And we actually have a project where I think for the first time ever, we have an IRB protocol for software that tries to befriend students. Okay, that's fairly novel, we think, and we'll see how that goes. So I just want to end by saying, look, we really think everybody ought to be using Analogie. And so, hey, SME's been publicly available since like the 1980s. The current version is at that link there. It's got documentation and a large set of benchmark examples if you want to build your own implementation, if you're allergic to common Lisp. But if you just want to kick the tires, there's a case mapper executable that works across different platforms, and it's designed to be cognitive scientist friendly. If you want a large-scale knowledge base to use in experiments, we have one of those too. So NextKB, you can download it from there. The ontology is distilled from OpenPsych. It's got full microtheory support, so you can have context. It's got links to FrameNet for semantic translations and large English lexicon. All the work we do on qualitative, visual, and spatial reasoning is there. There's some procedural attachments you'd need to make all the reasoning work, but the basics are there. And there's text files for building your own KB infrastructure. And there's executables. Case Mapper is running NextKB, but also CogSketch is a free download. And they both have socket interfaces. So for instance, if you want to plug those into a program for a quick experiment, you can use the sockets interface. And they're both licensed as Creative Commons attribution only, so you can do whatever you like with them. Okay, thank you for listening. Any questions?
Thank you very much for that, Ken. That was really, really interesting. If anybody has any questions, if you could raise your hand by going to participants at the bottom, and there should be a raise your hand icon, or if there's not, there's 3 little dots, and the raise your hand will come up, and then we'll invite you to ask your question and turn on your microphone. There's something in the chat. So I don't know if you want to ask this yourself, Priya, or shall I read it out? So they're great talk, thank you. I was wondering if you could say more about how Companion's NLP automatically builds structure representations from verbal input. I thought this is a difficult computational problem, only approached but not successfully solved by hierarchical Bayesian models.
Oh, yeah, well, so it turns out most of the successful natural language systems that are in use either use hand-tooled grammars that have been tuned for over decades or machine learning models. To my knowledge, hierarchical Bayesian models haven't been deployed in the way that these other systems have. For example, there's a thing called lexical functional grammar that was developed by Ron Kaplan and others as a linguistic theory. At the turn of the century, I got muted somehow.
Sorry, that was my mistake. I'm really sorry.
Okay. So PowerSet that Ron Kaplan started was the first group to parse the entire Wikipedia into a semantic representation. This was back in 2007. They won't tell me, how long it took, how many machines it took, right? A couple of days, but how many machines is another question. That parser, every time you do a query in Bing, you're hitting that parser. Okay. In Google, so the same year that the PowerSet people did their parsing of Wikipedia, a friend of mine at Google said, we're never going to do that because, hey, these parser people are always fiddling their parsers, blah, blah, blah. Within 6 months, I had dinner with the head of the deep language understanding group at Google. And they were, in fact, parsing everything, okay? And so there's a ton of parsers out there, some of which are very, very good. So we're using Alan's parser. We have our own hand-built grammar. And if you think about what happens here, the parser produces a syntactic representation. And tied to the grammar is how to combine the semantic constituents, right? And so those combinations basically propagate up the semantic information. And then you have choices. So you have polysemy words, and you have syntactic ambiguity. And all those are explicitly represented as choices. So the word packed in these things means I've got an explicit representation of the sets of alternatives without actually generating out all the concrete examples of it. Okay. If you have to generate the whole set, there's an exponential number of them, everything falls apart. If you try to prune locally based on probabilities, sometimes that helps, but sometimes it backfires badly because things that are locally okay together, in fact, really lead to a different interpretation. So in our system, it's producing these packed descriptions that then the system uses context in some form or another to disambiguate. So in query cases, it's saying, well, given the questions someone's asked me before, then these are the likely interpretations. And so it's doing abductive explanation, but the abduction is based on experience and being applied by analogy to new situations.
Okay, we have a couple more questions.
Great.
So I'm going to ask the first person who wanted to ask a question to unmute themselves so that they can ask it.
Hello, Professor Forbus. I'm Haleung. I'm a Ph.D. student in computer science and psychology in UC San Diego. Great talk. I love it a lot. I have a question. I think a large part of your talk is about like when we already have a structure mapping engine, we can do lots of amazing things. But my question is there an algorithm that models how the ability of analogy making is learned over time?
Well, so here's an interesting observation. Okay, so you notice how we said that the structure mapping processes seem to be operating from medium level vision up through conceptual change, okay? Now, think about how many orders of magnitude in time that is. So it's probably not all implemented the same way. So the matches for visual processing are probably, if you will, baked into our hardware, right? Baked into the meat, okay? Whereas using analogy and reasoning, if you look at it historically, so Dedry Gettner and some of her colleagues have done this, looking at, for instance, alchemists. The alchemist notion of what was similar was just crazy by modern terms. So analogy as an explicit construction is something we had to learn. Okay, so we're using the same model for both of those purposes here as a kind of engineering approximation. So companions wouldn't go through a stage like the alchemists of that kind of craziness. Might be fun to model someday, but so I do think that there are some structure mapping processes that are just baked into us. They really are that basic.
And we have another question from Anya, I think it is. Apologies if I've pronounced your name correctly there. If you'd like to ask Ken your question.
Yes, thank you so much. My name is Angie. Thank you so much for the talk. I guess I'm just really curious about the slide when you were talking about the continuum of knowledge, because like on the one hand, you have knowledge that is super concrete and on the other end is abstract. But I'm just wondering, is this like the idea of abstract versus concrete basically is just how directly or how perceptually available the information is? Because I feel like the idea of abstract can be applied to a lot of different metrics. Is there like a domain differences in terms of like what abstract means across different domains?
So that's a great question. So let me address the abstractness question first. So think about a coffee cup. Okay, so there's a particular coffee cup, and I have experience pouring stuff into this particular cup, and I know that if I'm too eager in the morning because I'm desperate for coffee and I pour it too full, bad things are going to happen. Okay, and so there's what it looks like in this particular case of overflowing, and there's more general. And it's going to be like some region out here I have to worry about, but out here I don't have to worry. So that's an example of a kind of qualitative model you may have abstracted away from several concrete experiences. And so as you go, you get to more abstract notions of containment, right? And those more abstract container metaphors may still actually have some bits and pieces of the concrete stuff. So there's work by Dedry and one of her students, Anya, whose last name I am going to mispronounce so badly that I will not even try. But the idea is, in some spatial prepositions, even in very abstract usages, there's still small numbers of concrete attributes there that haven't been totally worn away, which argues for an analogical abstraction account. Now, for domains, so one of the hypotheses that's worked out really well in physical domains is qualitative representations. Do those also apply in social reasoning? Oh, I think so. So you think about an action that's going to endear you to someone. You've accidentally insulted a friend and now you're trying to make amends. Do you know that if I do this particular nice thing, it's going to be 0.72 improvement in our relationship? And if I do this other thing, it's going to be 0.43? No. But you may know that this is like a bigger thing than the other, and so you're going to do that because you feel like you really, accidentally hurt this person. And so we're continually using ordinal judgments in trying to evaluate our actions. And so I think those qualitative descriptions apply to social reasoning too. Probably also mental reasoning, self-models. So in psycholinguistics, you say versus ah, right? So you say when it's going to be a little bit longer to generate an utterance than the interlocutor would expect. And you say, ah, it's going to be a lot longer. Humans metacognitively are not always that accurate, right? So when Herb Clark was talking about this, obvious question to ask was, well, are there ahs and ah-ums? And he said, oh yes, absolutely. Okay. And so we do have some sense that it's going to take longer, and that's not a conscious sense, right? Because, I mean, the people doing speech recognition systems are not stupid, but for a long time they actually filtered out those disfluencies, which weren't telling us anything, but they're actually signal. And so there's a lot of unconscious processing we do that's exquisite in terms of its use and timing and in terms of its overall accuracy, but not perfect. The fact that there's something in our head that can do ah, and ah is pretty staggering when you think about it.
Thank you. Does anybody else have any questions at all? So we've got a question from Sean here. Sean, if you would like to ask a question.
Hi, Ken. Great talk. This is hopefully a quick question. You mentioned that for the Q&A training, the model can actually specify sort of the most impactful cases to train on for future iterations of training, right? So I was wondering if you looked at sort of the most adaptive training sequences with respect to sort of the psychological literature on how to get people to make really disparate analogies or how to sort of detect some of the most deepest relational structure, and if there's any sort of congruence between how people tend to learn and how the model tends to learn.
So we have not looked to see if that training sequence would also be optimal for people, in part because the so we're currently exploring the hypothesis that this analogical QA training could go a lot further. That is, for a lot of dialogue act detection, for a lot of basically every place where right now we use what's called narrative function. Narrative function detection in some of our experiments done by hand-coded rules. So in moral decision problems, you're looking for what's a dimension along which I'm making a decision, lives, money, right? And then I'm looking for protected values. And so the system knows it's looking for those things, and it only makes abductive choices that are going to give it stuff relevant to that. So that notion of narrative function is great and does seem to capture something about what we're doing in the high level. We're letting the task influence semantic interpretation, but we don't want to be writing those things by hand, right? So something that's trying to learn much more of those things. For instance, C.J. McFate, who graduated from us recently, and he's now at Elemental Cognition, was looking at learning constructions, right? So construction grammar by Dale Goldberg and Mike Tomasello, they've argued that structure mapping gets used in learning language. And so CJ was actually trying to model some aspects of that. So I do think that is very promising. And so being able to use analogy all the way up and down the spectrum of representations that people use to understand language makes a lot of sense to me. A lot of work to get there, though.
I have a question about the overall architecture, if I can. So SAGE and Structure Mapping Engine and MacFac, am I right in thinking that these are discrete kind of processes that operate separately? And do you think that? No. Okay.
It's a stack. Okay. So think about it this way. SME is used in all three. It is one of them. MacFac consists of a first stage it's MapReduce, right? It's MapReduce with content vector dot products over everything in memory in parallel, where content vectors are automatically produced from structured representations. And then the second stage is MapReduce over a handful of outputs with SME. So MacFac uses SME. Now SAGE has what are called generalization pools, which are its model of a concept, and it has one of those per concept. So like word sense disambiguation, star, astronomical body, star, famous human, those are two generalization pools. And it uses those to do disambiguation. So you get the word star, it takes linguistic context, uses MacFac to retrieve, and whichever pool it comes from, that's the interpretation it uses. So Sage uses MacFac, MacFac uses SME, and Sage also uses SME to mush things together. So if I'm adding a new example, it's using SME to compare them, and it's using those correspondences to update the properties of the generalization.
Thank you. Do you have any thoughts on how they would map onto concepts from somebody who comes from a cognitive or developmental psychology background? Does Sage, is that part of the conceptual system, or is MacFac to do with procedures?
Well, I think of these as both psychological processes that are operating in us. So Sage, by the way, there's actually, we actually figured out around 2014 that in addition to these things happening in long-term memory, there's something similar happening in working memory. So Arena's models of analogical theory of mind, they actually use the working memory version of Sage, and can make some quite clever predictions based on that. So this is like stuff we think is in our heads. It's not declarative that you have to interpret every time, right?
That's my question. So we have a question from Hyro. Do you want to answer ask your question, Hyro?
Yeah, a wonderful talk, Professor Kenneth. Thank you for sharing your knowledge. I am just asking about, I think a structural mapping engine use these abstract representations like syntactic ones, but maybe it is necessary to have more concrete representations, like, for example, lines or simple forms that maybe are not so representable as syntactic things. And I was wondering if this software considers these kinds of representations, or do you think it's not necessary, or they are too much difficult to implement? Your thoughts about it. Thank you.
Yeah, well first let me say, if you said syntactic, that's a slight misconception. So these are structural, and they're very much semantic relations. So object acted on, that's not just like an arbitrary node that actually has some meaning in the language system, right? And so the visual examples I showed you with geometric analogies and ravens and oddity, those are all using automatically produced relational representations from visual inputs. And so we actually think for vision, the same thing gets used, literally the same thing. In fact, Kaizen Chen, one of my students, has a paper in AAAI last year where he showed that you can take visual inputs from things that are hand-drawn sketches, but take bitmap images, automatically produce line representations, which then CogSketch uses and learns to recognize them via analogical generalization. And so we really do think the same processes are occurring in vision. And if you want to experiment with that, download CogSketch. So CogSketch doesn't have the hardcore vision stuff built in, but you can sit there, draw whatever you like, and you can see what CogSketch produces for it in terms of representations. And if you turn on the developer and experimenter flags, you can actually draw two things and have it compare. In addition to, I mean, there's a whole bunch of stuff we built in. Andrew Lovett spent a lot of time on this to help people explore how those visual representations work. So by all means, download it and kick the tires.
Thank you.
Okay, does anybody have any final questions before we wrap up at all? No. Well, thank you very much, Ken, for that really fascinating talk. It was
Well,
really
thank you all for listening, and thank you for the really great questions. That's how I measure the success of a talk. Interesting questions.
brilliant. Yeah, and thank you everyone for turning up. Just to let you know, next week we have Dr. Iwaz Dimute from Birkbeck, who is going to be talking about relational reasoning from a neuroscience perspective, and also looking at science and maths and relational reasoning as well. So please do come and join us next week. Just to let you know, this video will be on the website probably later today or tomorrow. There's a page on there now for videos, so go there and you can have a look. But thank you all for turning up, and that's bye for me, and thank you.
Happy trails. Bye-bye.
Thank you.